right, good morning, everybody, to this Thursday where we start our next chapter, which is the start of our calculus material, which means things might be a little newer and you have to scale your study time and preparation accordingly. We've done some review topics, some things you remember well, some things you perhaps do not remember well, or we are doing it in a slightly different way, perhaps. Regardless, the things that I addressed and the way that I did them is ideally the way I want to um, see things moving forward. As always, can I just get confirmation in the chat that everyone can both see and hear me? All right. So today we sort of have a crossover lecture. If you um, watched what we did yesterday, was it yesterday? No, it wasn't. Well, yeah, yesterday. Wow. We our last example sort of left a couple of questions instead of answering everything perfectly. Where when we look at long-term behavior, it's not always as simple when it comes to vertical asymptotes. But one thing at a time, we want to get our language sorted out first. All right. So let's remember. Actually, let me just give this heading. First, we are in um, topic, I'll call it topic 2 on limits. And I've given enough time for this topic. Ooh, my head is really big. That's okay. I've given enough time for this topic so that you can ask questions, we can take our time and just see all the little variations that there may be because we are not taking a formal technical approach to limits. It's very hard to do that and it's just not necessary for us. But the downside is that we want to give enough time with enough examples to get a feel for what we're trying to do here and what could happen and how we handle it and so on. And it'll be good enough in the end. We don't need to be too technical. It sort of takes us away from our focus. So let's remember long-term behavior, the long-term behavior question, or finding a horizontal asymptote, if there are any. What was that question? Now let's just do it for a polynomial. Why not? Or let's do an example for each. Not a problem, just an example. It's random polynomial. We said that if x, for example, approaches infinity, then I may want to find out what does negative x cubed plus 2x minus 4 do. That's a typical question that we ended with last time. So now I'm looking for how this function behaves. It behaves like what? As x behaves a certain way. Now, not behaves like necessarily the word like, but it behaves in a way that it's growing. So this arrow indicates behavior. x is growing indefinitely. Let me emphasize maybe just behavior, not behaves like, but you can phrase it in different ways. And then I want to know what is the behavior that the function exhibits when x does this. Now, we've identified that if it's a polynomial, we can simply look at the leading term and say, well, this polynomial behaves like its leading term, which is a much simpler function. It's a basic transformation of, well, that's not it's a transformation of one of our basic functions. We can easily figure it out, and we can therefore answer this question without doing much at all. If we just know how to look at it and what it's asking, that it's going to be negative infinity. So the y value, the function value, blows up in size but always negative, as x blows up in size but always positive. I simply want to now phrase this in a more compact way that going forward it's going to feel a little bit more like calculations instead of sentences, but it's going to be the exact same thing. Okay? I want to introduce this question, and I'm going to leave it open because what the answer is changes things a little bit. The sentence, the question is going to be the same. I'm going to call it, I'm going to give a temporary sentence and then the mathematical symbols. We're going to call it the limit of negative x of my function, whatever that may be. And then I need to, of course, say what is x doing as x approaches infinity in this case, right? And we're going to slowly look at variations. And now I'm just going to make this a little bit more compact. And we're going to write L, or maybe a prettier L, L, I, M for limit. I'm going to say underneath that the behavior of x. And then I'm going to have my function maybe in brackets. Maybe it's just a function name, whatever the function is, right? And then I'm going to ask, what is that equal to, right? So this question mark is now the same. Okay. So there are three cases. Let's say here, case 1, case 2, and case 3. And we're going to do examples and see what the answer could look like. Oh, -4. What does it matter? It's just a random example. Sure, fair enough, fair enough. -4. Fair enough, fair enough. Okay. So now the answer could look different depending on what the function is, depending on what the behavior is. And slowly we'll see all the variations. We'll see that the function could, sorry, not the function, this answer, this behavior could, uh, let's say here, answer is a number, like a 0 or a 1 or a 3 or something. Then we say the limit exists and it equals that number. But in other cases, the answer, like in our example here, is a plus or minus infinity. Infinity is not a number. Remember that if my answer is infinity, then I don't have a horizontal asymptote, right? It doesn't approach a stable y value. It keeps growing up or down. So even though it seems like I have an answer, that answer is just an indication of behavior. Technically, I only have a proper answer if it's a number, if I get, in this case, a horizontal asymptote. So we could say a little bit more about the behavior with a plus or minus infinity over here, but we still say the limit does not exist because it's not a number. Okay, so I want to make that clear from the start that there is a slight difference. We have information about the behavior, but the information isn't quite stable. It's not a horizontal asymptote. It doesn't give me a specific number. It's not going to a specific number. There's information, but technically we're going to say the limit doesn't exist. Only exists if it's going to a finite number. Finite. Okay. And then we'll see eventually there's no answer. There's nothing we can say. Then we'll, of course, if we don't have an answer, then nothing exists either. So that'll be the more clear does not exist. And we'll see examples, but we have to wait a little bit for those weird cases. Okay. So I want to have with this limit for notation, language, word, I want to just have a more compact version of the sentence we are familiar with. If I can just see limits in the right way, there is nothing weird or scary about them. And we've seen this sentence of behavior, this question of behavior already. We should be more comfortable with it now. The limit, when x goes to infinity, is not anything different. It is just a rephrasing of that same question, of that same sentence. Okay. So now, if we maybe take a rational function, we have more options in what the answer could be. Because for a polynomial, it's always going to go up or down. It's just a question of which one. Is it a positive infinity or is it a negative infinity? That's a property of the polynomial. So we'll never have a limit existing, even though we'll be in this second case of how our answer could look. But when we change the function, then we have more options for what our answers could be. So let's see something like that. Actually, I did have a problem question. We might as well do that now, actually. Instead of me making random examples, we actually have one. Let me make a new page here, and I want to look at problem 2.1, number 6. Number 6. Where all I need to do is, the question is now going to become evaluate the limit. But there's no difference in the question. The question is still, what is the long-term behavior of this polynomial? Nothing is changing in the question. People get a little flustered when they see, oh, evaluate the limit. Ooh, what does that mean? It's just a new version of saying the same thing. So we have the limit. X approaches negative infinity. What was my function there? 5x minus 3x cubed. Put brackets around it if you want to. I don't really care. So now I see what kind of function is this? It's a polynomial. That means, and my behavior is asking when x gets large negative, then I know polynomials behave according to their leading term. So I simply need to look at what this leading term does. We can actually say, if you want to link it to how we said it before, we could say when x approaches negative infinity, then 5x minus 3x cubed behaves like negative 3x cubed. Now, all we're doing is rewriting this sentence. Whenever we see limit, we are talking about behavior. So this is asking, what is the behavior of this polynomial? Well, it's the same as the behavior of negative 3x cubed. So the sentence is exactly the same as what we're saying with this limit word. Nothing is changing. As soon as we have limit, we're talking about behavior. Anything you write in the limit, you can write out in a more wordy sentence. Nothing is different. I want to emphasize that. People think as soon as they see limit, they need to do something weird. No, we're just rephrasing the behavior question. And in that question, we looked at the essence of the polynomial. Long term is its leading term, which is basic as transformations of a basic function, the cube function in this case. We can easily evaluate what that is doing. Well, it's going to be an infinity, right? It's up or down. The question of how many negatives do I have here? Well, x is negative itself, so 3x's gives me 3 negatives. With the negative 3 in front gives me 4 negatives, so positive infinity. Now I write an equal here. Don't uh, read too much into this equal. Don't read into this equal sign. That does not mean the limit exists. It's all about what my answer is. It's just a verb in the sentence. If we say the behavior of negative 3x cubed is infinity, then that equal sign is just taking the place of a verb. It doesn't mean this is equal to a number. The limit technically does not exist because for a polynomial, we didn't get a number. It's not going to stabilize to a number. But we put an equal sign because that's like the verb in the mathematical language. So it would be weird to not put an equal sign there. So the equal sign is, everyone agrees that that's the appropriate symbol, but and don't confuse yourself and think that that means it exists. It depends on what the answer is. So I put an equal sign there. Even though I don't have a limit existing, I want to indicate more behavior. I have more information that the graph of this polynomial is going to go up eventually. So there's some more information I want to indicate, and the equal sign is the easiest symbol to use there. Doesn't mean it exists. It's all about what the answer is. Okay, so an equal sign is appropriate. There's nothing else I could really use there. Just replacing the word is as the verb. Okay, but let's look at something more interesting where we're always going to get infinities when we look at polynomials, right? So we're going to have to change the function if we want to see other kinds of answers. Polynomial is maybe a little bit boring for this kind of question. So I want to do problem 2.1 and I want to do number 10. Look at a rational function. Maybe that's going to be a little bit more interesting. So limit x goes to infinity. Not a problem. That means I'm looking at my familiar long-term behavior. I have the function in front of me here, x cubed minus 6x plus 4 over 3 minus 4x cubed. Okay, so now this is at least a little bit more interesting. So let me just make clear here, backtrack here. In our sentence version, oh, I don't have arrows there either. The behaves like will be mathematically an arrow. The behaves like words are now, these words are now captured in the limit. And this limit means the behavior of dot dot dot, whatever. So it wouldn't make sense to say the behavior of negative 3x cubed behaves like infinity. That doesn't sound right. I would say the behavior of negative 3x cubed is infinity, and therefore the equal sign is more appropriate because the behavior words are already being translated. Okay? It's all a translation issue, really, when you think about it. And that makes it less scary once you learn the language. It's all learning the language, right? I'm not saying anything new. It's all just the grammar of it, really. Okay. But we have to, of course, get that grammar and language down. Fair enough. And we'll see it over and over and over. Really, don't worry about the first example is always going to be a little weird as I get used to the language. Okay, so now I read this in the mathematical language, and I'm translating it to English. And it's asking, this is my function. the behavior of this function as x grows in size is what? I can write my, um, let's call this y, just for convenience. I can write my wordy sentence and say, as x gets bigger in size, I'll just conveniently do that, y behaves like, well, that depends on what kind of function it is, right? And because it's a rational function, I look at the ratio of leading terms and it behaves like x cubed. The top polynomial is dominated by its leading term because x is really big. Bottom polynomial, its leading term, it happens to be second, that doesn't matter, behaves like that. So now this is this exact same sentence. The behavior as x blows up of that function is the same as the behavior of x cubed over negative 4x cubed. I can simplify this, and then I get a negative 1 over 4, which is consistent, which is stable, which is a number. And I can then say the limit exists in this long-term behavior question. Let me move up a little. In this long-term behavior question, the limit existing is equivalent to finding a horizontal asymptote. I don't really care exactly how it approaches that line right now. Sometimes it's a lot of work to figure out. Later on, we'll have tools to easily do it. So one way or another, it is approaching that horizontal line when all the ups and downs are done. So the y value is stabilizing I can make it as close, the y value, I can make it as close to negative 1/4 as I want by just going far enough to the right. It has very predictable, stable behavior. And the limit is trying to ask, do I have that sort of stability? Now this one, it depends on what x is doing. In this case, x is going far to the right. And then it's asking, is the y value honing in on a specific number the further I go? And we, by identifying it as a rational function in this case, we've been able to figure out, yes, it's going towards negative 1/4, stable. The further you go, the closer it's going to get. So I want to emphasize that. We can get as close to, we can get y as close to negative 1/4 as we want by letting x get larger. You want to say, oh, I want to be within 0.001 of negative 1/4. I can do that. I just need to take x far enough and I'll get there. Someone else might say, no, 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 I want to be within 0.000001. Sure, I just need x to be bigger, and eventually it'll get so close as I want. It'll never get there. It's a behavior. It's not an equal. The y value for large x values won't be equal to negative 1/4. It's just going to get as close as I could possibly want it to be, and then closer, the further out x goes. Okay, let's just have a little pause here and see how that feels. Understanding that the limit is not at this stage a new concept for us. It's simply a rewording, a translation of this long-term behavior we've seen already. Not new. Okay. I cannot emphasize that enough. People get so intimidated by limits, and I feel it's because they don't understand what it's actually asking. In simple words, it's asking for the behavior of the function as x does some stuff. Okay. Any thoughts or questions so far? Okay, now this is our introduction to limits, and I don't want to overwhelm you. There's when you look back 3 days from now, I guess over a weekend, so 4 or 5 days from now, it's gonna seem like there are so many different cases, so many different things that could happen. So I want to build that up slowly in a somewhat logical manner. And though no books would ever do this, I feel the first step to in this is by way of this long-term behavior question. It's not my fault no books do it in the best way. It's their problem. One day when I feel like it, I'll write my own book, but that's a lot of work. I'm kind of lazy. I like talking about it more. Okay, so now we we're not restricted. Let's notice something. We're asking for behavior. The graph has the function has many x values. We are not restricted to just infinity. We're not restricted to x going plus or minus infinity. Why? There are other interesting things that I want to perhaps investigate or say something about when it comes to the behavior of the function. I could take a polynomial. Let's take f of x, and let's make it nice and simple. X squared plus 2x plus 1. That's a polynomial. There's nothing wrong with that one. Could make something easy. I already know what this function looks like, right? Uh, Whether you do or not, it doesn't really matter. It sits over there, nice parabola. Whee! Oh, that was backwards. Sorry. Let me make this a minus, since I've already drawn the graph. That's the guy I want. Doesn't actually matter. Whee! Oh, it's not a bad parabola. Sitting there at 1. Y-intercept is 1. Everything super straightforward, I hope. I might want to ask, so I could ask the behavior of the function as x gets really big, then this translates to the limit x approaches infinity. F of x is my function. I can just look it up really on the graph. It's infinity. So I'm indicating behavior. Okay, it's not a number because it doesn't stabilize to a horizontal asymptote, right? So not a big deal. That's one question though. Okay. But we could ask other questions. We might ask, let's suppose we don't know the graph. We don't know the function. It's weird. We might ask, how does this function behave as x gets close to 0? Maybe I want to know that. And then we could rephrase that by saying it's the limit as x approaches 0 of my function. Of course, what the function is the deciding factor for what the answer is. I then look at my function. I see, oh, it's a nice parabola. As I approach 0, or around x equal to 0, the y value, let's pick a color. Let's make this colorful. Let's go pink. Why not? As I am around this 0, getting closer and closer, the y values, I'm sort of traveling along the graph like do, 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 do. As I get closer, I'm coming down on this side, or I'm going up on the graph on this side, which means my y values are honing in on 1. And there's nice, stable, predictable behavior. If you're interested in getting closer to 0 for x, y is just going to get closer and closer to 1. No problem at all. Limit exists because the closer you bring x to its target value, I'll never get there. Remember, it's a behavior arrow. It's not an equal. I'm never actually at 0. It's a different kind of question. I'm asking, if I get closer and closer to 0, does the y value have stable behavior getting closer and closer to a specific number? Yes, it does. Look at the parabola. I'm going to slide closer and closer along the graph to the y-intercept as close as you want by just getting x closer and closer to 0. Limit exists. Okay, that's the basic concept. I have to have a graph that I can sort of slide along around the point of interest, the x value that I'm interested in, but I'm never going to get there. Now in this case, this 1 is exactly the x value. Sorry, is exactly the y value when I plug in that x value. So it's not a very interesting question to ask about behavior when I have a y value. I can just plug in the x value. Sure. The behavior covers that and perhaps more if there are interesting other features of the graph that we'll slowly see for other functions. Okay. So in the simplest case, the behavior question isn't really a strange new question. If I have a nice graph, I have a y value, it's going to be as simple as just plugging in the x value. Now, I don't want to make a big deal about this, but that's going to happen when my function is continuous at the x value. 0 in this case, right? It could be any number. I just used an example of 0. What do I mean by continuous? Well, informally speaking, I can draw the graph without lifting the pen. It's nice and one piece. And as x gets closer to its target value, I am really just traveling along the line, whatever the line is. There's a line, there's a graph, I travel along it to my target y value. Okay, we don't have to define continuity in any formal way, I don't think. Well, I know. All right, so is everyone happy with sort of the boring case that I just want to get out of the way? That if there's a nice graph, I can travel along it around the target x value, then the behavior is very stable. It's going to go to the corresponding y value. There's not any issue here. The behavior, the limit concept isn't really designed to care about that. It covers those basic things, but it's really there for when weird and interesting things are happening with the graph, with the function. But I mean, one thing at a time, one thing at a time. Right now, I'm getting used to the limit being a translation of the behavior question. Sometimes that behavior question is a little silly, right? I can just plug in the x value, right? There's no weird behavior happening here. But I could still ask it if I really wanted to, right? If you really want to ask for behavior, sure, but I'll just plug in the x value and give you the y value. That is the behavior. But even in this boring case, the limit does still translate the behavior question. Okay. Now it just takes time, and we'll see many more interesting things where we can't necessarily plug in an x value, but we still ask the behavior. Those two things are not the same. For this function and this target x value of 0, the graph, the y value, is getting closer and closer to what its value is. And in this case, it happens to be the y-intercept because x goes to 0. If x goes to something else, I could do another one. If x approaches, let's say 1, then it's going to be the y value that I get there, which is 0, right? It's this guy. So if f is continuous, one piece, everything's good, then yes, if I ask for x going to 0, it's going to be the y-intercept. Yes. If there is a y-intercept. And in the case of a polynomial, it's just always going to be like this. So I could generalize this to any polynomial, let's say that first. If f of x is a polynomial, I know that it's defined for anything. Get rid of that line there. Get away from me, line. A polynomial is defined everywhere. Then I could say the limit question as x approaches any c, any finite number, 0, 1, 1,000, what do I care, is going to be the y value that I get when I plug in that x value. Because this polynomial is continuous, uh, let's say here for all x values. Everywhere it's continuous on the whole number line. There's no strange behavior that a polynomial has. It's the simplest basic function. It's one piece graph. I can draw it with one. If I had the skill, I could draw it in one go, never lifting my pen, never doing anything strange. Any x value that I'm interested in approaching, the y value will just go towards the corresponding y value to the point on the graph. Nothing strange is happening. So the limit just covers the basics. Where there is no issue, I could still ask a behavior function behavior question if I really wanted to, but it's kind of silly because it's just plugging in the x value. Okay. Now, okay, so we've covered the basic, the idea of it being a translation from one language to another, the basic situation where it's just a y value, no issue. I just want to show how the behavior is an interaction. I'll say it like this very informally. You won't find any book saying this. The limit or the behavior. Ooh, that was a U. Ooh, that's ugly. Yeah, get rid of that. The limit or behavior question is, yeah, I'd say it's mostly, I don't want to say always, it's mostly about the interaction of the components of the function. I don't want to say factors because it really depends. I guess you can call it factors. Yeah. Sure, you can call it factors. The things that make up the function. It's really a matter of how they interact that determines the behavior of my function. We've seen this with the rational function, right? For example, let's look at a problem. I just want to make a new page for that problem. Again, this is very much our introduction, and there's so many little things that I need to mention. It's tricky to find the perfect order to do them in. But we'll have plenty of time to look back and fill in any gaps that you might have. 2.1, I want to look at number 12. Number 12. Oh, there it is. Hello, number 12. Okay, so I have a limit. And I have 2x squared plus x minus 3, x cubed plus 23x randomly plus 1. I just want to make a side note since I forgot to really explain the heading of this problem set, infinite limits. When x approaches positive or negative infinity, we call them infinite limits. That does not mean the answer is infinity. The answer could be anything. It's about the behavior of x. Let's let's say it over here. Long-term behavior, infinite limits. That refers to x approaching plus or minus infinity, not the answer, not what the function, not what the function is doing. Oh, I got all choked up there. It's so beautiful. Infinite limits, I feel, is a good starting point because it's just a continuation of the long-term behavior question that is the easiest question, especially for polynomials. So this is an infinite limit. That in no way means the answer is infinity. The answer could be many things, especially as the function gets more interesting. I understand what this is saying now. This is asking for the behavior of this function as x gets really big positive. I identify it as a rational function, which means all I need to do is look at the behavior of the leading terms and how they compare. You don't have to write this middle step. But because we did in the sentences, this function behaves the same as the ratio of its leading terms, that's exactly the same sentence. I've just translated it. I then have an easy way to look at this. 1x left at the bottom. So I could even go a little further. Well, this behaves the same as 2 over x. That's one transformation of the basic rational function, and that's going to be a 0. If I get an answer of 0, does that mean the limit exists or not? Exists or does not exist? That is my question to you. Exists or does not exist? 0 is a number, limit exists. Sure, 0 is perhaps a special number, but it is a number. It is finite. The limit exists. Horizontal asymptote will be 0. All those things, they're all related, right? They're all related. The leading terms, because it's a rational function, I just need to look at the leading terms. 2x squared at the top, x cubed at the bottom, 2x's cancel with 2x's at the bottom. I have a 2 left, and I have an x at the bottom. And I know because it's a transformation of my basic function, which is why we did those, that's going to go to 0. Okay. But we've seen with rational functions, especially, it's all about how these pieces interact. So now I'm saying that in general, that's true as well. It's how the pieces interact. And a lot of can that can tell me a lot about how the behavior, what the answer is to the behavior question, what the answer is to the limit. So to figure out or to help me figure out how these pieces interact, I'm going to look at what I call the form of the limit. These are things you're not going to find in a book, and it baffles me why they're missing, because they're extremely helpful. So helpful, I cannot live without the form of the limit. But let's just backtrack and check the chat question. Which one did I miss now? I think yeah, people said existing. They answered my question with a question, but I'll let that go. The limit exists because my answer is 0. Then one person asked, wait, how is 2 over x 0? Because x blows up in size. And we have done, you could take your, I don't want to do it on this page. I want to do it over here. You can take your y equals 1 over x, whoop, whoop, boink, boink. Oh, that shouldn't touch. Boink. Right? I have the properties of my basic function. That transforms to 2 times 1 over x. What happens? It stretches out a little bit. What happens when x blows up? It's right there. It's heading to 0. So I'm reducing my original question to a question on a function that is a transformation of something I should know extremely well. I don't know what this original function looks like. No idea. But I know what 2 over x does. I know everything about 2 over x. Wait, why is 2 over x equal to 0? It is not equal to 0. The behavior is 0. The behavior of 2 over x as x approaches infinity, that is 0. I will never say 2 over x is equal to 0. Very big distinction to make. If the denominator blows up and the numerator stays the same, we've talked about this, then the whole thing shrinks down to 0. I am not saying the function is equal to 0. Never, ever, ever. It takes time, but definitely ask questions. That's why we're here. I'm just trying to catch up on the chat. So it'll equal 0 if it's any number over x. Absolutely. No, no, no. Well, it depends on what x is doing. They fit together. The behavior of x causes a behavior of the function. I need to see them together. If x is blowing up in size, if x approaches infinity, then any number over x will shrink down to 0. But x can do many other things as well. If x is going towards negative infinity, then it's all about the size. Then the size is still increasing. Any number over x is still going to be a little fraction. That little fraction is always going to be negative, but it's going to shrink closer and closer to 0 still. It's all about the size of x, either infinity, and a number over x will shrink down to 0. So, I mean, it's a good time to emphasize again how I don't want to sound arrogant in any way. This is not my goal. But everything I'm saying is important and we will most likely use it again in the future. That's why we looked at the basic rational function first. We slowly build these concepts. I've talked about long-term behavior of 1 over x. And then I asked, what happens if we multiply 4 and have 4 over x? And everyone said that no, the behavior is the same. So we've done those things, and it's very important that you are very clear on what happens in the lecture, because chances are we're going to use it again. And we want to then have new concepts. Now the limit is a new concept we're focusing on. We can't now have the behavior of 2 over x be shaky as well. It just makes it much more complicated than it needs to be. It's okay if it happens, but ideally you want to build your foundation in the correct way so that we can focus on the new parts and not be confused by things that happened a week ago. It's very important to build this up to give yourself the best chance to succeed. Let's check the chat here. If x is going towards negative infinity, I've answered that. Still 0, but then I'm just going to go, where did I graph that? Over here. Then I'm just going to go over here. Still heading to 0, but just a little negative. A little negative. And again, everything I'm saying is important and will probably be used again. But then when it comes up again, we don't want to struggle with that and the new concept. That just makes it so much worse, so much worse. Anyway, okay. So to emphasize in our last few minutes here, to emphasize the interaction of the pieces is not always so easy. So now, the form of this limit. What do I mean by that? I'll make it pink. Color is always helpful. I have a numerator, and then I have a denominator. I am now, when I talk about the form of the limit, I'm not right away attempting to answer the question. I'm simply asking, how do these pieces behave on their own? Forget that they're combined in this function. Just how do they behave? How does the pink guy behave? If x, of course, approaches infinity. Well, that's just a polynomial. Its leading term is 2x squared. It's going to approach infinity. Again, we're building on our discussions of polynomials that have to be solid for this to be as easy as possible. How does the blue polynomial behave just on its own, as if it was a completely separate question? Well, its leading term is x cubed. X goes to infinity, so it'll go to infinity as well. Infinity. So now I see that the interaction of these two pieces is they're both increasing in size. And it's a question of how fast are they increasing. If one is increasing faster than the other one, it'll eventually dominate the whole thing. Infinity is not a number. I can't just say, oh, I'm going to cancel the two infinities and it equals 1. No, no. No. Maybe he has a nose. He should have a nose. Okay, that's not the case. All I'm saying is sometimes when I look at the pieces individually, they could highlight what is happening and they could not. In this case, I have an infinity over infinity. We call that an indeterminate form because it doesn't really tell me how the whole thing behaves. It's all about how each piece, how fast each piece blows up. That'll determine the interaction. So then I need to go and say, okay, at least I know I need to be careful. Infinity, infinity over infinity doesn't really tell me much. Now let's go and see, oh, it's a rational function. Okay, so let's look at the leading terms. And it turns out that the bottom one dominates, shrinking the whole thing to 0. But if these two were flipped around, they still both grow, but the blue one grows faster, and the result could be very different. Okay, let's look at. I guess I should stop, but I don't want to. I'm so close. I want to do this last one because that's sort of my point of this whole form thing right now. And again, I'm trying to introduce concepts like the form of a limit early because it's going to come up again and it's, in my opinion, extremely helpful. Number 8 is the limit x approaches infinity 1 over root x minus 100. That's not a rational function anymore. What do I do? Leading terms? What's the leading term here? I don't really know. It's not quite the same. The form of the limit can very often show what is happening here. Well, the numerator is always going to stay at 1, right? Nothing's happening to it. There aren't any x's in there. What is happening to just the bottom guy? Just the denominator. That is a transformation of my basic square root function. It's the square root shifted to the right. Let's draw it. Here's my basic square root, transformed to shifted to the right. Which way is it going when x gets really big? Infinity. Basic transformation. Basic function. Now I have a situation, even though the function was something that I didn't know what to do with, it wasn't a rational function or anything, I have a situation very similar to this guy, where I have a number over something that blows up in size. It doesn't matter what makes it blow up in size. If the numerator doesn't match it, the whole thing is going to shrink to 0. 0. I don't need to know the details of this function. It's not a rational function. Who knows what this looks like? I don't know. And I also don't care. By looking at the pieces separately, very often, not always, but very often, it can shed some light on how the whole thing behaves. If the numerator stays constant at 1, but the denominator keeps getting bigger, then the whole thing is going to be a fraction that shrinks down to 0. It doesn't matter what the function looks like. So by looking at the form of the limit, I'm looking at how the pieces behave separately, and if that could shed some light on the overall behavior. And very often it does. Of course, we need to look at this in with a lot more examples. Tomorrow is a discussion on its own, but the idea of the form of the limit is going to come up over and over. It is so useful. I cannot stress how useful it is. Even if I get an indeterminate form of infinity over infinity, that still tells me, okay, be careful, go look at the type of function and try and do something else and see what you could do. Even a word of caution is information that helps me. And sometimes it's so useful, it gives me the answer right away. This is not an indeterminate form. An indeterminate form is one where the form does not tell me the answer. Look at this. This indeterminate form came from this rational function, but if I flipped it around, let's note here, if I looked at the limit, same x behavior, but I flipped the numerator and denominator. Plus 23x plus 1 over 2x squared plus x minus 3. The form is still infinity over infinity, right? They're both individually going to infinity. They're polynomials. However, the answer to this limit, when I look at the behavior of the leading terms, it's going to be infinity because there are more x's at the top than at the bottom. So even though the form is exactly the same in appearance, the answers are very different. Different answers. So an indeterminate form, informally speaking, is when the form does not give me the answer right away, and many things could still happen. And we'll see that the only indeterminate forms are infinity over, well, for us, there are others. For us, it's infinity over infinity, 0 over 0. We'll see 0 over 0 tomorrow. Those ones, really anything can happen because it's all about how they interact with each other, how fast they grow, how fast they shrink down. Other forms, like 1 over infinity, it's not called a determinate form, but I guess you could. It's just not an indeterminate form. I guess you could call it a determinate form. That sounds weird, though. No one uses that. Sometimes the form gives me the answer right away. Boom, it's 0. Has to be. I don't care how fast this is growing to infinity. If the top one doesn't even remotely try to challenge it, the whole thing's going to shrink down. It doesn't matter how fast it happens. But I, I don't want to go on a rant, but if you read calculus books, even life sciences or more formal calculus, doesn't even matter. They don't give enough attention to what we're really doing here. It's all an interaction of the pieces to investigate the behavior. And sometimes it's super simple. There's nothing to do. And sometimes it's not, and I have to be careful. Fair enough. But it's all about looking at this in the most efficient way. What is this really saying? What are the pieces in my function? How can I use those pieces to get more information to see which way this is going? If I just look at this in the correct light, it really doesn't have to be complicated. And it baffles me why I don't know of any textbook that does it this way. And they make it so much more complicated than it needs to be. It doesn't need to be complicated. If we just remember that we're investigating behavior, and of course, the pieces of the function will determine that behavior. And now it's just a matter of seeing all the little variations and building up our experience to not be surprised in a future problem. Of course, this discussion needs many more days. We can only do so much in our time, but think about what we've said. These concepts will come back tomorrow and the day after, and then hopefully over time it'll get better and better each day. All right, that is all we have time for today. Sorry for the random rants. They weren't random actually, but still. I apologize for going over time, but hopefully things slowly make sense.